Welcome, everybody. My name is Ilya Mandel. I'm one of the general members here at the Aspen Center for Physics. Now, you're all, of course, very fortunate that I'm not actually the person speaking today. You have a far more handsome and charismatic speaker in Enrico Ramirez-Ruiz. In addition to being very charismatic, Enrico, of course, has many other skills. He is apparently a phenomenal salsa dancer and a championship kayaker, and along the way, a damn good physicist. Enrico did his PhD with Martin Rees in Cambridge. He was the Bahcall Fellow in Princeton, and has now for a number of years at the IAS, I should have said, now for a number of years has been a professor and occasionally department chair at the University of California, Santa Cruz, as well as spending some time in Copenhagen during part of this period. Enrico has a great many awards and honors. He is a member of the Academies of Sciences of several different countries. I'm not going to list all of them because you'd much rather listen to Enrico than to me. I think the main award and honor that Enrico has, though, in my eyes, is that, according to my wife, he is her second favorite astrophysicist. By the way, just to be clear, I'm not on the list. So without further ado, over to Enrico.
Wonderful. Okay, thank you. It's an honor being here. I want to thank the organizers of the colloquium for inviting me here. I also really want to thank the staff at the center who make all of this possible. We wouldn't be here without them, so I'm incredibly grateful to them. I wanted to highlight my collaborators, the work that I'm going to talk to you a little bit about, and give you a little bit of an outline of what I'm going to do. So I'm going to tell you about nuclear properties and the R process, just broadly speaking, hopefully in a pedagogical way, to give you some grounding of the questions that we're looking for. At the same time, here we're currently in a wonderful meeting called Stellar Interaction. Two neutron stars merging is the stellar interaction that we looked at. And I have highlighted some of the folks that are in the Aspen Center right now that are experts in these topics too, so that you start associating them. And a lot of them have done incredibly transformative work on this topic. And then I'm going to tell you what we know from abundance observations in stars, from high resolution spectra, which basically inform our models. Then I'll move to talk to you about neutron star mergers as a side of our process, nucleosynthesis. I'll explain what our process is. There's a large number of folks in the audience and currently at Aspen that have worked a lot about how these objects are assembled, how they evolve, how they merge. I'm really going to focus more about observational signatures, and hopefully I can convince you that in fact we have detected the signatures of our process material being basically catalyzed in one of these mergers. We have detected these incredible events, so I'll tell you a little bit about lessons learned from that. And finally, just to make it a little bit more personal, I'll tell you about how our process nucleosynthesis is linked to planet habitability. And in order for us to understand that we owe our process material being here, I'll tell you a little bit about chemical evolution. So how these metals ultimately mix in the universe is actually essential to understand planet habitability. So this is the outline of my talk. I'll dive right in. So this is the abundance pattern of the sun. This is sort of the periodic table of astronomers. The first thing that you notice here is, of course, the odd, even variations that you see. But more importantly, when you look at this pattern, you immediately realize that abundance peaks are intimately linked to nuclear structure, in particular these neutron and proton closed shells, determining very, very interestingly where those peaks lie. So the things that you notice here is, of course, neutron closed shells and the proton closed shells are independent. Yeah? So these magic numbers, you can be doubly magic, like lead, for example. And the other thing that you start realizing is the break of symmetry in the sense that as elements get heavier beyond the iron group, they require a larger number of neutrons in order for them to be stable. This is pretty apparent here. And then you see some peaks there that are at first sight appear not to be correlated with nuclear structure, but what I'm going to actually show to you is that they are. And these are the R process peaks. So, the vast majority of nuclei above the iron peak, and this is because, of course, charge reactions cannot catalyze these elements, are basically catalyzed by neutron capture. And when you capture a neutron, you, of course, create a heavier nuclei, which then beta decays. So when we refer to S or R process, is slow with respect to the beta decay timescale. So if you capture neutrons faster than the beta decay timescale, that's what we call the rapid process. And if you capture neutrons slowly, that's what we call the S process. And what is shown there is basically the peaks, the abundance pattern peaks. And I hope I can give you an intuitive understanding of how these three peaks arise and how the R process peaks seem to be shifted with respect to the S process peak. Okay, so in order to do this, I'm going to spend some time in this beautiful plot, which is reproduced here in this Needham review. So what we show here is the proton number versus the neutron number. The first thing that I highlighted there is the stable nuclei. That's the beta stability valley. So of course, you're doing the S process, you're moving very, very close to beta stability, and you follow the stable nuclei pattern, okay? Another important thing to highlight there is that as you move out of equilibrium, the lifetime of these nuclei becomes progressively shorter. You can see that there. And it also shows there what happens when you capture a neutron. So you capture a neutron and then you beta decay and you move in that direction as shown there in the diagram. Now, illustrated there, which is important, is a typical R process pathway with separation energies of a few MeV. The first thing that you notice is that our process patterns are basically capture neutrons very, very far from equilibrium, and they have to happen incredibly promptly. If you look at the timescales there, you realize that you're in tens of milliseconds territory. Okay? So you have to capture neutrons at a speed that is about tens to hundreds of milliseconds. Now, as an astrophysicist, you will say, well, what compact object has dynamical timescale of the order of tens of milliseconds? And the only answer is a neutron star. Therefore, that's why neutron stars, either when neutron stars are actually formed or when neutron stars merge, provide you both the timescales, but the high density of neutrons that you need to actually capture these neutrons fast enough. Another important thing to highlight here is these closed neutron shells, these magic numbers. Something quite interesting happens there, of course, because these nuclei are more stable. They don't want to capture neutrons. But to illustrate this, let me give you, these are neutron capture cross sections of nuclei in the S process pathway with neutron energies of the order of about 25 electron volts from the Clayton textbook. The thing that you realize is that odd mass numbers tend to have higher cross section than even nuclei. So you immediately remember that pattern variation between odd and even nuclei that you see in the abundance pattern. The thing that is actually pretty amazing is the substantially lowering of the cross sections near the magic numbers. And as a result, the idea is that abundance anti-correlate with neutron capture cross section. So the way that you can think about this, you can think about if you have a neutron flow, as soon as you reach those magic numbers, you get a stagnation of the flow. And therefore, you're going to get an increase in abundance at that particular magic number. Another way of thinking about it is if these neutrons are like in a highway and you basically get stagnation and a collision, then all of these cars will basically pile up and then you will get an abundance peak at that particular position, okay? So abundance anti-correlate with neutron capture cross sections, and it starts giving you a feeling about how these peaks form. So what I highlight here is if you're going through the S process, you're going very, very close to stability. So you reach the first magic number, second magic number, and the third magic number there. So you get your first, second, and third peak. And because you're close to stability, those peaks coincide with those magic numbers. But imagine that you're going through the R process pathway very, very far from equilibrium. You get your first peak, second peak, and third peak. Then you beta decay back to stability. So the peaks here, as you can see, are the projection in that plane. And that nicely explains why is it that the third, the three peaks from the R process are shifted to the left when you actually look at the total mass number. That doesn't mean that, they had basically memory of nuclear stability, but of course that's forgotten once they decay back to the stability. So they don't coincide with magic numbers, but we know that they did when they were formed because they were formed far off of stability. And that gives you a feeling of how these three peaks arise. So something important to highlight is about half of the elements are made through the S process, half the R process, but particular elements, the vast majority of them are made by both of them. You can think of lead, for example, which is primarily an S process element. There's a contribution of the R process. So I have highlighted here first, second, and third peak of the R process. The third peak is my favorite. It's a really pure R process peak, and of course has platinum and gold. So both are primarily pure R process elements. And I have highlighted europium there. Europium is in a rare earth peak element, but europium has an oscillation strength atomically that produces basically an absorption line feature in the spectra of stars that is, as I will show you, incredibly deep. So we use europium as an indicator of the content of our process in stars. Okay. So I'm going to talk to you a lot about the first, second, and third peak. And we refer to the heavy R process as the second and third peak. Okay. What do we know from our process observations? So this star doesn't look like much, but it's now referred to as the Sneeden star. And is the star, it's a low metallicity star, but relative abundance of our process is incredibly high. Yeah, it's the relatively highest enriched star in the universe. Yeah, the relative abundance of gold of this star is incredibly large. What we have learned from high spectroscopic resolution spectra of these low metallicity stars is that our process pattern is incredibly robust. What you're seeing here, these stars have actually been arbitrarily shifted in normalization. So this doesn't tell you the total amount of our process material that each of those stars have, but they tell you the abundance, the ratios between element abundance compared to the R process abundance of the sun. And what you can see is that the R process abundance of the sun provides an incredibly robust description of the R process. So what we know from that is that the R process has been operating incredibly robust since the universe was, a small fraction of its current age. In addition, it tells you that whatever astrophysical process you come up with, you shouldn't really drastically depend on the initial conditions, and you should converge to an abundance pattern that is relatively robust. So that gives you significant amount of constraints when you think about how to make the R process. And then I'll tell you a little bit more about the variations of our process from star to star. That's also important. Remember that the pattern is incredibly robust, and what I'm illustrating here is the pattern of the heavy R process. So this is between the second and third peak. And we know that the first peak have, it's less robust than second and third peak. So when we think about variations of stars, so what astronomers like to do is they like to use these units, which are logarithmic units, and they divide by the solar abundance. So in this plot, if you're in 0, 0, that is where the sun lies. And as you move to lower metallicity, something that has -4 has 1 part in 10,000 of the metal content of the sun. Okay? And what you see is basically europium as a tracer of our process divided by iron. And you see that the fluctuations of europium are incredibly large as a function of metallicity initially, And then those fluctuations from star to star actually damp slowly. And we'll talk a little bit about why that's the case. But just to illustrate, I want to actually guide you through two stars that have very similar abundances, iron abundances, but they have very different R process abundance, just for you to kind of pictorially look at how how astronomers actually make these measurements. So, for example, here these two stars are compared. One of them is this Neutron star. If you look, I have highlighted there calcium. So you can see that the calcium content of these two stars is relatively similar. Something also that it's incredibly beautiful is that you can see how you can actually do progressively higher resolution until you get to incredibly high resolution. And I want you to look at 4130 Armstrongs to see the europium feature. And then you compare the depth of europium of these two stars, and you drastically see difference in R process content between those two stars. Even though they have similar metal abundance, their R process variations are high, are almost by a factor of 100 their content of total R process. Now, in astronomy, we use total metal content as a proxy for time, because after the Big Bang, we primarily had hydrogen and helium, and astronomers call anything that is not hydrogen and helium a metal. And then the metal content of the universe increased, primarily through stellar processes and stellar interactions. So as a function of time, the total content of metals in the universe increased. When we looked at these low metallicity stars, they're actually early old stars in the halo of the Milky Way.
You haven't told us what an R process is, and how do you decide something as an R process?
Yeah, so the question was, I haven't told you what an R process is and how you can decide how much. Yeah, so the argument is, you have to capture neutrons quickly. You have to converge to this abundance pattern. And I will illustrate to you how to make it in a neutron star merger to give you an insight of how the material that is ejected in a neutron star merger actually turns into our process. And then how that incorporates into the gas, and then ultimately into stars. So I'll guide you through that process. Yeah. I'll show you in real time so you can see it made. Now, if you want an order of magnitude understanding of our process production in the universe, a galaxy like our own, the Milky Way, forms, has a star formation rate. That means it's forming stars at a rate that it's about 1 solar mass per year. On average, over the entire history of the Milky Way, it's made about 1 solar mass per year. Now, the sun has 10 to the minus 7 of its mass in our process. Yeah. So as an order of magnitude estimate to guide you, the production rate of our process in our own Milky Way has to be of the order of about 10 to the minus 7 solar masses per year. So that's ultimately what you want to match, and it gives you a fairly robust lower limit of whatever mechanism you want to invoke to produce the R process. You have to basically get a total mass production rate of about 10 to the minus 7 solar masses per year. And then just to anchor your thinking, supernovae, as an order of magnitude in our own Milky Way, happen at a rate that it's about once every 100 years, 10 to the minus 2. That means that if every single supernova will produce the R process, particularly after explosion and as the neutron star is cooling, you will require a mass production rate of about 10 to the minus 5 solar masses per event. So 10 to the minus 2 multiplied by 10 to the minus 5 give you the magic 10 to the minus 7 solar mass per year, just to anchor your thinking. Now, of course, neutron star mergers are significantly rarer because you have to make neutron stars and then you have to wait for them to merge. So the rate order of magnitude is about 1 every 10 to the 5 years. So that means that in order for them to be a viable production avenue for the R process, you have to produce of the order of about 10 to the minus 2 solar masses per event. Yeah, so that anchors your thing. And a lot of what I'm going to tell you about is that these two production rates are going to leave very different imprints in the stellar abundances of stars in the Milky Way. Yeah.
100,000 years is per galaxy?
Per galaxy, yeah, like our own Milky Way. Yeah. So it's all of these are sort of normalized at star formation rate of about 1 solar mass per year. Now, there's a simple argument that you can make for how much mass per event you require. And these basically comes from the fact the vast majority of these low metallicity stars were actually enriched by, on average, 1 event. So the question that you can ask is how quickly I can turn the ejecta. For example, if you have a neutron star merger, you inject both energy, momentum, and mass. You say, well, how long it takes? What's the fastest that I can turn that ejecta into stars? And the first constraint that you have is that you have to cool the material. So this remnant has to go through a cooling phase, and that gives you, that's the fastest in principle that you can turn, and it gives you an extra limit. So the argument that you can think about is how much hydrogen you have to sweep in order to start cooling, and then you say, well, how much mass I can put there to actually explain the abundance that I see of europium over hydrogen of stars at low metallicity. That gives you a very, very simple argument. And what you realize, particularly, you can clearly see this Neutron star has so much our process that it requires a minimum amount of mass per event, that it's 10 to the minus 3 solar masses. If you put less than that, you were not able to get the enrichment levels that you see. And remember, here we're being incredibly conservative because this is the fastest that you can turn these ejecta into stars. In fact, you actually have to sweep significantly more hydrogen. It actually tells you that the total amount of our process that you need has to be higher. Now, there illustrated is sort of the core collapse supernova rate. If core collapse supernovae were producing the R process, they cannot go beyond that line because ultimately they will overproduce the total 10 to the minus 7 solar masses per year. And as a result, just looking at the abundance distributions of stars, you get an incredibly strict constraint that these events have to basically be produced at a rate that is significantly lower than core collapse supernovae. Either you have an incredibly rare core collapse supernovae, or you have something like a neutron star merger. Okay. And this is just simply what we know from the abundant distributions of low metallicity stars. So this suggests that the production of heavier process elements needs to operate robustly and at a drastically reduced rate when compared to core collapse supernova. So then the argument is, I'm going to focus on neutron star mergers and how we think our process is produced in the systems. There are many stages in the interaction of a neutron star merger where mass is ejected. The first, as I will show you, is the tidal ejecta as these two objects come together. There's some arguments that as these objects actually touch and heat up, there's material that can be ejected above the escape velocity. Ultimately, we believe this remnant will collapse to a black hole, and we also think that the accretion disk could be a source of our process. Now, the material, as soon as the merger takes place and neutrinos are produced, nucleosynthesis becomes significantly more complex. So I'm actually, just for this talk, I'm going to just focus on the tidal tail ejecta, just to give you an insight of how the R process is made in the systems. So to illustrate this, I'm going to show an archaic simulation, which did in collaboration with Stefan Roswell when I was a PhD student. So this is just to give you an insight of the tidal tail ejecta. So here you have two equal neutron stars. They have equal mass. They are basically brought together by the emission of gravitational waves, which, as you know, carry both energy and angular momentum from the system. These two objects come closer together until the interaction tidal potential becomes so steep that they basically merge. And what you're going to see is the mass ejection in the outer Lagrangian points as these two objects merge. And what we're going to follow thermodynamically is actually what happens to the mass ejecta that is actually able to make it above the escape velocity, which is of the order of about 1% of a solar mass. About 1% of a solar mass of material you get above the escape velocity in these tails. Of course, the field has evolved dramatically from the simulations, and we now have general relativistic calculations with MHD, and hopefully soon full neutrino transport in order to understand the fate of this event. Okay, so I spent some time giving you some insight when you think about protons versus neutrons. I'm going to highlight a few things here. So this is from Skynet, from Jonas Lippener. So what you're going to see is the results of an R-process network calculation, which has neutron captures, photo dissociations, alpha and beta decay, and fission reactions. At the top here, it's illustrated the time. So you basically are following these tails as the function of time. And illustrated there is basically the temperature in red. So of course, as material is expanding, you're adiabatically cooling, density, and the energy rate reduction as a function of time. On the bottom there, you actually show what is the current composition of the material as a function of time. So you actually see the R process production in real time. Now, what is incredibly important is this material is incredibly neutron rich. You can see there Y is 0.1. So that means that nuclear statistical equilibrium, you have tons of free neutrons, but you also have nuclei. And you can clearly see there, you already have the targets ready to capture those neutrons. And what you're going to see is basically that capture. Yeah? So very, very far from equilibrium. As we talked about, you reach the magic numbers, you get stagnation. Illustrated there are the first, second, and third peak, and then the decay back to stability. Now, we are now 50, or so seconds, a minute after, and you continue to decay to stability. So for astronomers, this decay is incredibly important because it is ultimately what's going to power the light curve. Yeah, understanding that decay is essential. And as they decay back to stability, that's ultimately what it's fighting against adiabatic expansion, and it's basically continuously heating the material. And as you can see, the abundance pattern has actually converged at this stage. I'll play it again. So you can see there's a peak in the energy generation rate, the time scales of about a fraction of a second, and then the energy generation rate decreases as a power loss, a function of time. So that gives you an intuition of how the R process basically evolves as a function of time, and what is the distribution of the composition in the material. Oh. So just to give you a cute insight, you choose gold, which is about 4% of the total mass of our process. One of these events produce about a Jupiter mass of gold. So you can, 1 gram of gold is about $10, so you can do the calculation. But more importantly, what gives you some insight is that one of these events can contribute to the R process content of millions of stars. And so you have a process that is incredibly rare, but produces a significant amount of mass. And we were going to see that this is going to have incredible implications for how stars ultimately get enriched in the universe. And that gives you a feeling of that production. So just to summarize, when we think about neutron star mergers, we think about, of course, the secular evolution that is driven by the decay and emission of gravitational waves, which last anywhere between hundreds of mega years to giga years. These systems evolve slowly until they become, significantly closer. They become dynamically unstable. In this particular case, I illustrate a mass ratio that is not of order unity. In that case, you only have one tidal tail. You have ejection in the outer Lagrangian point. These last a few milliseconds. Remember, few milliseconds is the kind of expansion timescale that we're looking for because we want to capture the R process. And we're fighting against that beta decay timescale of tens of milliseconds. So we have R process element production in the tidal tails. Again, happens very, very quickly. And then you get both the expansion of the material, and then you get nuclear heating of the outflow, both in photons and particles. And as long as the material is optically thick and the stopping length of both particles and photons is small, the size of the object, you're basically heating up that material and you're fighting against basically adiabatic expansion until at some point you become close to transparent, the photons are able to escape. And that's where you ultimately see a peak in the luminosity. And this happens of the order of a few AU, which, AU, it's to the 13 centimeters or so. But we're familiar with it given our own solar system. Yes.
So, and the neutrons produced in this process, they're later absorbed by other objects, by stars to form heavier elements, or they're absorbed already inside this mirror?
Yeah, and they are already prefabricated. So as process elements we think are actually built inside stars, but our process elements are built in this kind of really high extreme conditions of density and temperature. They're ejected into the interstellar medium and they're basically become part of stars. I'll show you that. But then they're not furtherly processed inside stars. Of course, the temperatures and densities of stars, they're not able to actually do anything to this element. But as I will show you for the Earth, the content of these elements is really important. Okay, so when we think about creating or producing a light curve, how ultimately these explosions turn into radiation, we think about initially we have this radiation-dominated compact ball of free steam and ejecta. This is Arnett sort of pioneer some of this thinking. You have adiabatic cooling. So adiabatic cooling, it's taking away your internal energy because you're expanding. Radiation is also taking away your internal energy because photons are diffusing away from the material, and that depends on the diffusion timescale there indicated. What it's incredibly important for us is that you need a heating rate. You need to basically battle against these sources, that are taking away the internal energy to continue injecting internal energy. And here I show you some calculations by Luke Roberts, in which he shows what is the energy generation rate per unit mass of our process material as it decays. And you remember that you saw that the energy generation decayed as a power law. The reason that it's a power law, this is basically the contribution of a particular element to the decay. And because you have so many elements, ultimately you get a power law, which was predicted by Lee and Paczynski. These sort of calculations allow us to actually calculate what is the power law decay of the energy injection. And I'm going to give you a little bit more insight as to why this is incredibly important to do. So the argument is that the bolometric luminosity, the total radiated energy emitted, follows the heating rate. And you can see that, for example, in the type 1a supernova model, which is ultimately powered by the decay of nickel to cobalt to iron, you can clearly see in the dashed line, that's the heating rate, and that's the light curve calculation of the bolometric light curve of a type 1a supernovae. So initially, this luminosity increases because the material is basically optically thick. You expand until you become transparent, you get a peak, then you go back to that decay. And what is shown there is what we name kilonova models. Kilo because they're order of magnitude 1,000 times brighter than a novae, so we call them kilonovae. And what you see there is that, broadly speaking, the bolometric light curve of this model should follow the heating rate. So that was one of the first observational signatures that we were looking for if we were to detect these systems. Now, something that makes the calculations incredibly challenging is that we have to understand the opacity of our process material. We need to understand the atomic structure of these elements, which is not simple. And as you know, atomic complexity doesn't depend solely on the number of electrons, but it depends on the way that you can basically arrange valence electrons in the last shell. So we clearly know the F shell nuclei are atomically much more complex. They have significantly larger number of line features simply because they are atomically more complex. And then the question that we think about is, well, how's that going to impact the light curve? And just to give you a feeling, these elements in the periodic table are between the second and third peak the R process pattern. Yeah, so they're heavy R process nuclei. So some of the fairly novel work that Dan Kaysen and Jennifer Barnes did at Berkeley was to actually think about how can these atomic complexity ultimately show up in the light curve. Just to illustrate here, if you take an F shell element compared to a standard iron element, you can see that the number of lines, it's larger by an order of magnitude. So when Dan Kaysen and collaborators started thinking about this idea, they say, well, we don't know every single oscillation strength of every single one of these transitions, but we can try to explain them statistically on average. And what is shown there is basically the opacity of photons to D shell nuclei versus F shell nuclei. And the thing that you realize is if you only had D shell nuclei, you become transparent close to the optical, and the vast majority of the light actually escapes at optical wavelengths, which for astronomers is actually incredibly convenient because optical telescopes are significantly more sensitive than infrared. But if you have F shell nuclei, you are basically opaque all the way into the infrared. So that was basically another important constraint, that if the heavy R process was made, that means elements between the second and third peak, the opacity of the material be so large that you expect the vast majority of the radiation to emanate at infrared wavelengths in the red. And these were the type of models that were made in anticipation of the discovery, where basically you illustrate there is the Lantadine fraction, which tells you what fraction of the mass is in this F shell nuclei. And as I increase the fraction of these F shell nuclei, what you see is that the spectrum becomes progressively redder. So, something in the optical basically have no F shell or very small contribution, and as you increase that. So another important component was that if we know that the R process is incredibly robust. These neutron star mergers are to be a side of our process. They better produce elements between the second and third nuclei, the second and third peak, and this was basically an expectation of what we were going to see. Now, another interesting feature is, in addition to have these millions of lines, these lines are actually broadening by the velocity. So when you actually look at the spectrum, you see these really broad features, and actually the broadening tells you something about the expansion velocity of the ejecta, illustrated there from 1% of the speed of light, 30% of the speed of light. These broadened features become incredibly prominent. So if you were to do kind of like a autocorrelation, you will be able to actually extract on average the velocity of the ejecta. Okay, so that was the theoretical foundation that we had at the time that LIGO discovered this incredible event. So I'm going to guide you very broadly of the features that we see of these. I wanted to highlight that I was incredibly lucky to be a member of the 1 meter 2 hemisphere collaboration. Numbers were not very inventive with names. We had 1 meter telescope in Northern California, 1 meter telescope in Swope. You don't actually know if an event is going to happen in the south or the north. So we cover both hemispheres, and I was incredibly grateful to work with this amazing group, which is led by Ryan Foley, who's here in the audience, who basically took the first image of the photons associated with the gravitational wave signature. Something I'm very proud is, of course, I'm the oldest individual there, and we had an incredibly diverse and early career team at Santa Cruz. So this is what we saw. We saw initially that the transient was relatively blue, and then it turned red, as expected. So broadly speaking, can we ultimately get an estimate of the minimum mass? Well, if the bolometric, one of the things is, does the bolometric luminosity follows the energy injection rate? The answer is yes. Broadly, there's some uncertainties about how you do bolometric corrections at late times, but that gives you calorimetrically a minimum mass. So the minimum mass that you actually need in order to produce the total light that you see is about 1% of a solar mass. Again, that 10 to the minus 2 order of magnitude. Now that's of course minimum because the efficiency of turning that heat into radiation is not of order unity. So you need a mass that is probably a factor of about 3 or 4 larger. That gives you kind of a simple estimate. And in addition, the fact that the power law matched the R process decay is an indication that yes, R process decay and this production back to stability is actually powering the Lie curve of the system. So our process is being made. So just to give you a feeling, from the LIGO rate, very order of magnitude, you imply a Milky Way rate of about 25 mergers per mega year. Again, of the order of about that 10 to the minus 5 per galaxy we were talking about. Or estimates of the total mass, which are uncertain, are about 0.06, which means that you integrate all the cumulative mass of our process elements ejected from all past events that were all identical, which we know they're not going to be, it's about 10,000 solar masses. So that gives you kind of an order of magnitude estimate. If you multiply that by about 10 to the 7 or so, you get an estimate, that matches the total stellar mass order of magnitude. And importantly, what we saw is we require actually a 2-model component. Just to explain first the fairly blue component and then the red component. But what we saw is that we require at late time a significant fraction of heavy R process F shell nuclei in order to explain the spectrum, which became incredibly rare. So we know we have an estimate of the total mass. If you believe stellar spectroscopy, which I think you should, is one of the most important aspects of astronomy, and you know that our process is incredibly robust, you also are convinced that this event produced elements between the second and third peak. So it seems overall that these neutron star mergers are a viable pathway to produce, the R process elements that we have in our own Milky Way. So there's a lot of incredible science that this event has allowed us to do. I want to go into detail, but I wanted to sort of focus on the evidence for the cosmic creation of heavy elements. Okay, so the last of my talk, I want to try to give you some maybe insight as to why you should care about the R process. Well, if you care about gold and platinum, you care about the R process. But why the R process is essential to life? And what I'm actually ultimately going to show you is that our process elements are actually essential for Earth to create the magnetic field. So I'll guide you through that. Now, what is essential here is to really understand what is the R process variation from star to star in the Milky Way. Okay? To understand that, we have to understand chemical evolution. So I'm going to give you a fairly simple model of chemical evolution. But the motivation behind why we care so much about our process elements is that uranium and thorium in today's Earth contribute with the vast majority of the central heating of the Earth. And therefore, they're driving the convective motions inside the Earth. Yeah? Potassium-40 also contributes significantly, but potassium-40 actually doesn't go as deep the settling as uranium and thorium. So even though our process, these elements are 1 part in a billion of the total mass content of the Earth, they are actually the largest heating source of the Earth's interior today. What I want you to kind of think about is, well, you make a twin analog of our solar system. We expect any variations of our process from star to star at metallicities where planet formation takes place. And what will happen to the Earth if we have more or less our process content? So that's basically the question that I want to guide you through in the last part of my talk. So to do this, I'm going to give you a very simple chemical evolution model for you to think about. So let's imagine that we have our process production through type 2. Yeah? So we talked about, if we now know, challenge the notion that every single type 2 could make the R process. It can't, because they need to produce significantly more, but let's assume that they do. you have a process that is very, very common, produces a little bit of our process mass. Yeah? So the analogy there is that you can think of the Milky Way as a chocolate cookie where the chocolate is the R process, and the R process will be fairly homogeneously distributed in the cookie. Yeah. But if you think about merger production, mergers produce a significant amount of R process and happen rarely. So the model that you should have in mind is the chocolate chip cookie, yeah, where all the R process is very highly concentrated in particular regions. So the implication of that simple thinking means, well, if if a star is made from gas that was enriched close to the chocolate chip, it's going to have a significant fraction of R process elements. And if you're far away from the chocolate chip, you're going to have little. So that, the range of fluctuations that we see from star to star tells us something about the rate of injection of metals. More importantly, as these elements evolve and are spread out through the Milky Way, they're actually turbulently mixed. So you continuously produce and mix them. So you expect that those fluctuations slowly damp out as a function of time as you become more efficient at mixing these materials. Okay. So in general, this is what we see. When we think about type 2, magnesium is primarily produced by type 2 supernovae. Europium is produced either by mergers or by a supernova event that is incredibly rare. And this is what we see in the observations. If you look at magnesium to iron fluctuations at a given metallicity, they're small. And they basically change. One of the reasons why you see there that magnesium over iron changes is because type 1a supernova start producing significant amount of iron and basically lower the total magnesium content of the universe. But more importantly, look at those europium over iron fluctuations that are very, very large at a particular metallicity. Now, in order to understand this, people have employed a broad range of simulations. So there are simulations performed in a cosmological content. These are simulations by Jill Neyman. And then what you see there is, for example, of course, europium is chosen with a gold color so that you can actually see then the variations of gold in a galaxy like our own Milky Way. Then you can try to do global galactic models. Now, some of the problem is that the turbulent mixing time scale and scale is very, very small. So you need to actually do incredibly high resolution models to understand the mixing of elements, which are basically inputted by hand in a diffusion kernel for all the simulations. So what I'm going to show you is results of kind of high resolution simulations, just to give you a feeling of this mixing. So the way that you can think about this is imagine that you're taking a cross section of the Milky Way disk. So in the top is in this direction, at the bottom is in this direction, and you clearly see the iron over hydrogen. So iron is produced at these early stages by type 2. Type 2, it's very, very common, doesn't produce a lot of iron. The iron distribution is fairly isotropic, while the europium distribution it's basically very patchy. So there's large variations in the gas phase in europium over hydrogen compared. And ultimately, you can compare these two observations, and you basically can derive that the turbulent mixing puts constraints that the injection rate of metals has to be anywhere between 10 to the minus 6 solar masses per year versus 10 to the minus 5 solar masses per year. Now, one of the reasons why these production rates are in excess of that 10 to the minus 7 is because a small fraction of the R process material makes it to the disk. Okay? Neutron star mergers are happening far away. The material basically doesn't incorporate very efficiently, so you need to produce more in order to explain variations that you see. And these are just in two different environments, whether they're made in small galaxies or large galaxies, and you can put constraints. Now, for the kind of the tail of the story, we really want to think about those fluctuations at solar metallicity. And that's what you see. So stars like our sun have changes in the R process that are a factor of 2 or 3. That means that diffusion, turbulent diffusion process hasn't completely damped the fluctuations. And one of the reasons why is because if a neutron star merger actually happens in today's Milky Way, as it expands, it would still drastically increase its local contribution to the R process will be sizable. Well, if a supernova happens in today's Milky Way, by the time it actually starts cooling, it is not adding significant amount of metals compared to the metals that you have. So that is incredibly important because you can think about, well, if I make an Earth-like planet and I change the total amount of our process, what happens to the planet? That's the question that we attempted to address. And one of the reasons why, because if you change the heating rate, you change the scale and the strength of the fluid convection currents, which are incredibly important for, sort of like the alpha omega mechanism to actually amplify the magnetic field. So, we did some simple models, preliminary simple models, but the idea that we have is if you have significant amount of radioactive heating, so you just take the Earth and increase the total amount of our process by a factor of 2, you get significant amount of radiogenic heating, you get extreme volcanism, but the dynamo actually doesn't work. You get dynamo is not efficient just because the strength of the convective motions is just too strong. The Earth seems to be very special in the sense that it's able to make a magnetic field. But if you actually change the total amount of our process by a factor of about 2 below the current rate, you get very little radiogenic heating. You certainly will build a magnetic field, but for example, the planet will be geologically dead. It will have no volcanism. It is also thought to be an incredibly important ingredient for life. So in some ways, this is adding to the complexity when we think about a habitable planet, that ultimately the content of our process material in that planet makes a big difference. And what it's kind of mesmerizing is that the total amount of, the mass fraction of these elements in the Earth are very, very small. But because of their decay time scale, they're contributing with the heating. Okay, so I just want to end here, and I hope I can convince you that these neutron star mergers are incredibly exciting phenomena in the universe. I didn't have the opportunity to tell you about everything that we can learn from the gravitational wave signal, everything that we can learn from merger dynamics, and how the R process is made is significantly more complex than the story I told you. There's a lot of intrigue as to what are the various sites after a merger takes place where the vast majority of the R process is made, whether or not we could ultimately derive an abundance pattern that is incredibly robust as we see in the observations. And ultimately, we owe to that long decay lifetime of these R process elements that we can actually see light from the systems and detect them. And ultimately, if that was not exciting enough, maybe the reason why we're here is ultimately to a neutron star mergers. So, or maybe hundreds of thousands of neutron star mergers all mixed together in the gas phase. And I'll stop there and thank you for your time.
So is the solar system in some sense in some sweet spot regarding the R process, so it produces this habitable abundance of heavy elements? And if so, can you look for other places where such conditions are met?
Yeah, I think the question is, are we special or not as a solar system or not in terms of the total content of our process? I mean, of course, the question that we're asking is a little kind of, anthropological in the sense that, we are in the current Earth, it has a magnetic field, it has volcanism. Keith, who's going to give the public an amazing public lecture next week, can tell you that determining the abundance of our process elements at solar metallicity with enough precision that you can see whether or not there's a factor of 2 of 3 is still open for debate, that variation at solar metallicity. What we find in simulations is that, yes, you should expect those variations to exist. And the argument is yes. I think if you try to think about it statistically, based on current errors, about 1/3 of stars at solar metallicity will have an R process content that will be basically made terrestrial planets habitable. But of course, also the simulations that we run, the heating are just one dimension, and we need to do multi-dimension, magnetic field amplification. But the hint is there. The total R process content does matter for habitability. I don't know, Keith, if you want to. Just gonna question. Okay.
Very simple question. What is the best estimate now for the fraction of gold in the universe made by neutron stars?
Well, I think so the question was, what fraction of the total amount of our process is made by neutron star mergers?
Gold.
Of gold, yeah. But it's an R process element, so a heavy R process element. I mean, I would say the gold story is interesting, and I'll tell you a little bit about that afterwards. But the argument right now that people have is whether or not neutron star mergers are the only channel. One of the concerns that we have is that neutron star mergers may take some time to merge, whether or not they're able to enrich, very, very early metal, stars. And there are simulations that show that they can. There are simulations that show that you cannot do it. And whether or not you need a channel that is basically maybe a rare supernova channel that also contributes to the R process. If for example, if Keith goes and gives you the best estimate of the total, if he does a mass inventory, total R process elements stock in stars, because we only see them in stars. We don't see them in the gas phase because it's incredibly difficult to detect this in the gas phase. And it gives you a mass budget inventory. And I tell you, LIGO detected this rate, and we detected, and we infer this mass, and we multiply those. We can, in principle, say that neutron stars could, in principle, contribute with the vast majority of the R process. But of course, that is based on one event. Now, yeah, and the gold is actually an interesting story, because I was telling you, a lot of the R process elements actually, when the Earth was made, which was molten, sank into the center. So geologists for a long period of time thought, well, where does the gold come from that we mined? And one of the arguments is it actually came from the late bombardment, through basically asteroids impacting the Earth that increased the metal, gold content. And because gold gets highly concentrated at high pressures, then that's where gold mines basically happen. So I think it's preliminary to answer that question, but it seems like neutron stars have to be a prominent channel, especially at higher metallicity. Whether or not they're effective at lower metallicity remains to be seen.
Yes. So how do you understand the representation of the Earth in the formation of a rocky planet? So I could imagine that maybe there's a significant amount of variation in the amount of R process elements that get into a rocky planet, independent of the representation in the protostellar system.
Yeah, the question that it asks is, if you take a piece of the Earth, its abundance pattern similar to the solar pattern or not? The answer is yes, because we see that in meteorites and asteroids. So, when we basically pick up samples, we see that the abundance pattern is there and it's fairly robust. The robustness of the R process pattern is, I didn't talk about, but we have found stars that actually are not very robust in the second and third peak. The vast majority of them are. Now, because the R process are a really very small fraction of the total mass, it's very difficult that you will put it in a volatile or something like that so that you preferentially eject that material. There's some really beautiful calculations that people are doing by basically digging into the ocean floor and looking at basically our process variations as a function of depth, and we see that. So it seems like as the solar system is moving through the Milky Way, it's basically capturing our process elements in the form of dust, because that's the only way that they're going to make it through the magnetic field, and they're settling into the ocean floor. And we actually see that there's variations of the material that it's coming in towards the solar system as we move around, because as a function of depth, it's a kind of a time clock. So we see that too. We also see that the ISM, there's indications that the ISM is not, that it has intrinsic variations. Just exciting.
I have a question about so you showed high resolution simulations of kind of the R process being very patchy. And so one of the questions that I have always had with this is, how does that depend spatially on the location of the simulation? That is to say, the central regions of the galaxy, is it more or less patchy outskirts versus say a dwarf galaxy?
Yeah, that's an incredibly interesting question. So the question is, what about the patchiness of the gas as a function of the type of galaxy, the star formation rate, the galaxy environments? So for example, no simulation apart from the simulations that we have run are able to resolve the kernel, like in order to really understand the mixing of one of these events, need a mass resolution that it's about 1,000 solar masses. So that means that these very large cosmological simulations basically put a Gaussian kernel already inputting at that mass scale. They're basically not properly doing all the turbulent diffusion. Now, the calculations that we have where we're doing just a piece of the disk, the only thing that we can do is change the scale height where we inject the R process elements. But if you actually look at where we think process elements are at least coming from, if they come from a stellar process, then the calculations that we do are fairly robust. But if they come from a neutron star merger and you have the disk here and they're happening all over, this material basically happens probably in the hot phase. You enrich, that material has to come back to the disk, cool, and then basically make stars. And what we find, for example, in cosmological simulations is that a significant fraction of the R process material is preferentially ejected into the intergalactic medium. So we expect if neutron star mergers are producing a vast majority of the metals, those metals will be ejected into the intergalactic medium, and the intergalactic medium would be super solar in terms of our process. And then the question is, how do you see that in the gas phase?
Sure. I see your hand. I want to make sure somebody from a different group also gets a chance to ask a question. So yes, please.
So this follow-up, those simulations also include the R process uses coming from collapsars. Do you frequent collapsar events in your cosmological simulations, or is it just from neutron star mergers?
So we have done both. We have done simulate. Oh, so the question was, if we expect the R process to come from a rare stellar explosion, they're going to basically follow the gas, the cold gas, and they're going to follow the star formation rate. While if they happen from neutron star mergers, there's a delayed time scale and they move farther away from their place of birth. And for example, the calculations that I showed there are assuming that less than 1% of the core collapse supernova are producing the R process. So we have done that. We have done both calculations. And depending on the rate and the mixing, you get slightly different answers. But the uncertainties on the injection rate and the mass per event are large enough. Both can actually explain things fairly effectively, apart from whether or not mixing is effective in the very early universe. And now, for example, a big disclosure, and since Keith is here, we now think that the vast majority of low metallicity stars that are R process enriched came from satellites. Were not made in the Milky Way. The reason for that is that when we looked at the kinematics of these stars, they're actually in counter-rotating orbits. That means that now the challenge, as Keith was saying, is actually how we enrich our process kind of dwarf galaxies, which of course have weaker potentials. There's some arguments as to whether you can actually retain neutron star mergers or not. And as you know, smaller systems are not as efficient at turning gas into stars. So then you may require larger amounts of our process productions.
Yes, so I think people from this interaction workshop. Yes, please.
I wanted to ask about the last part of your story where you were talking about the Earth having the Goldilocks state of the dynamo. How do we know that uranium and thorium are the things that cause the heat at the core?
Yeah, so primarily our understanding comes from this figure.
Yeah.
So what it shows here is the energy injection, the radiogenic injection per gram, a function of time in the solar system, of all the elements. So early on, for example, when the solar system was very young, aluminum-26 was the major contributing of the heating rate.
How are these rods produced?
But we know the decay properties of these nuclei very well. Experiments.
If I know the lifetime of the nucleus, then I know when I run out of that nucleus.
And then if you look at timescales that are important for the formation of the Earth, the timescales that are important for life, then uranium and thorium are the major contributors, apart from potassium-40, but potassium-40 has some issues in the sense of where it's located in the interior of the Earth. So gravitational settling tends to basically put heavier elements deeper into the core than not as heavy.
Okay, I need to stop here, so.
Thank you so much.